All right, so like we said in the last video, towards the end there, we were going to prove that this weighted Euclidean inner product with the following two weights, 2 and 5, are an inner product. And again, this is just a matter of checking each of those four definitions, those four axioms for an inner product. So the first thing we want to do is check for symmetry. What I'm going to do is use the U and the V the way that I've defined them up here. I'm gonna actually let's do this. I'm gonna say let U equal U1, U2, and V equal V1, V2. That way I can work with their components. So to start with, we want symmetry. By definition, the inner product of U with V is equal to our first weight, 2, times U1, V1, plus our second weight, 5, times U2, V2. And then, because these are all real numbers, they have the commutative property. So I could also write this as 2 V1, U1, plus 5 V2, U2. This, however, is the same thing as the inner product of V with U. So symmetry in this case follows from the commutative property of multiplication with real numbers. 2. Now we need to check additivity. So this time what I'm going to do is look at U, actually I need one more. UV, I don't want to use W, let me use R. R equals R1, R2. All right, so I'm going to say let's do U plus V with R, like this. Okay, the definition of this, or by the way we've defined our inner product, this would be 2 times, now the sum of U plus V, vector U plus V, its first component would be U1 plus V1. And this is times R1, plus 5 times U2 plus V2 times R2. Okay, if I distribute the R in and then regroup some things, I could write this as 2 U1 R1 plus 5 U1 U2 R2. Notice that's grouping this term after distributing the R1 and this term after distributing the R2, plus 2 times V1 R1 plus 5 times V2 R2. The reason I'm doing this is because this is the same thing, this first set of parentheses here is the same thing as the inner product of U with R, plus this is the inner product of V with R. So that establishes that additivity property. 2 more properties to go. The third one is homogeneity. So we need a scalar. I'm going to say let K be a scalar. Then I'm going to look at Ku, its inner product, the inner product of Ku with V. So this would be equal to 2 times Ku1, that would be the first component of Ku, times V1 plus 5. The second component of U would be, after multiplying by K, would be Ku2. So this is going to be Ku2 times V2. 2 terms, each one has a factor of K, which means I can factor out the K. This is equal to K times 2 U1 V1 plus 5 U2 V2, but the stuff that remains in parentheses is just the inner product of U with V, so this becomes K times the inner product of U with V, and there's my homogeneity property. Last thing to prove is positivity. So we want to show that the inner product of V with itself is greater than or equal to 0, and that it's equal to 0 if and only if V is equal to 0. So to start with, let's compute the inner product of V with itself. That's equal to 2 times v1 times v1, so that would be v1 squared, plus 5 times v2 times v2, that would be v2 squared. And this is, of course, greater than or equal to 0 because both of these terms are non-negative. Okay, now it's the next part of this is an if and only if statement. It says, positivity says that we want to show that the inner product of v with itself is equal to 0 if and only if v is equal to 0. It's very easy to show one direction. If I say, suppose v is equal to 0, then it would follow, the v would equal the 0 vector in particular. Then each of these terms would equal 0, and clearly this would come out to just 0. So proving the other direction is the more, it's not even that difficult, but it's the more or less obvious way. So what I'm going to do is say, suppose this is equal to 0, okay? Well, using the definition, like what we have up here, that would say that 2v1 squared plus 5v2 squared is equal to 0, okay? If either v1 or v2 are not 0, then 2v1 squared is positive, or 5v2 squared is positive. And that's because I'm squaring this number. So unless let's take v1 for example, unless v1 is equal to 0, squaring that number produces a positive number. Multiplying by 2 produces another positive number. Similar for v2. If v2 is not equal to 0, squaring it gives me a positive number. Multiplying that by 5 gives me a positive number. So now I have the sum of two numbers that can't be negative, and if at least one of them is positive, then there's no way this is going to equal 0. So I could say, in this case, the inner product of v with itself, which is this, would have to be positive. This implies that v is equal to the 0 vector. Okay? So it's just checking each individual axiom for an inner product. The next inner product that we want to look at is the inner product on Rn that's generated by the matrix A. And this is still, even though a matrix is involved, the inner product is on the vector space Rn. It's not on the vector space Mnn. We borrow a matrix from that space, but the vectors that we're considering are in Rn. So what I'm going to say is that we have some specific matrix A that has been chosen here. Some n by n matrix. Then in that case, if I select two vectors from Rn and multiply A on the right by each one of these, so AU and AV. That's an n by n matrix times an n by 1 vector. The result of this is an n by 1 vector. And I'm dotting that with another n by 1 vector. So AU and AV are both in Rn as well, which means it makes sense to take their dot product, the normal dot product that we defined back in chapter 3. Because this involves a dot product, it's very easy to show that this would be an inner product as well, just by checking all of those axioms again. We're not going to go through a full proof of that, just because it would be too similar to the one we just did to be worth the time. But I will mention this, and your book mentions this as well. The inner product generated by these types of inner products generalize the weighted Euclidean inner products that we talked about before in this sense. So if I have a weighted Euclidean product with the following weights, W1 through Wn, one way of getting this exact inner product here is to think of it as an inner product generated by a matrix A, where this is the matrix A that's being used. A diagonal matrix where the diagonal entries are the square roots of the weights in order, W1, W2, all the way down to Wn. I'm not going to prove that here. You can look in your book for an example, and it's a good exercise just to try that on your own. Verify that this does, in fact, create the exact same inner product that we just talked about.